Chapter 10. Let's do it. All right, here we go. Chapter 10, which deals with radical reaction. So hopefully you remember that a radical, you would have seen radicals a little bit in General Chemistry 1 and things like nitrogen monoxide. Radical just means an unpaired electron. So unpaired electrons are what we're dealing with when we're talking about radicals. Let's see here. Radicals, a bond. If we have a bond between two atoms, it can be broken in two different ways. One way is a heterolytic cleavage, and that forms ions. The other way that it can be broken is homolytically. And when we break a bond using homolytic bond cleavage, we end up with a pair of radicals. So let's take a look here. Heterolytic bond cleavage, this is what we saw all the time in mechanisms, right? In an SN2, for example, you have a nucleophilic attack and you have a loss of leaving group. Well, this arrow represents the flow of two electrons. Remember, when the arrowhead is when it's double-headed, that means that you've got two electrons moving. And so where are both of these electrons going? Well, they're going on one of the atoms in that bond, so it ends up as an anion, and the other one is left over as a cation. When we have homolytic bond cleavage, we don't use a double-headed arrow. We use a single barbed arrow like this, and that represents the flow of one electron. Let me try to make it a little neater here like this. This is what we call a fishhook arrow, and that represents the flow of only one electron. And what we're doing is we're taking both of these electrons, but one of them is going to go to the Y and one of them is going to go to X. So you end up with two atoms that have an unpaired electron, and so you end up with a pair of radicals. So there you go. Heterolytic bond cleavage, the movement of two electrons, so that's a double-headed arrow, and a one-headed arrow, or a single barbed arrow is what we usually call it. That is representing the flow of one electron, and so we can end up with a radical. All right. Here we have a little more detail on those arrows. We have a pair of radicals. Again, anytime in Organic Chemistry 1 or Organic Chemistry 2, if you see double barb, it means you're moving two electrons. And if you have a single barb, it means that you're only moving one electron. All right, so I think we got the arrows down. And I mean, let's face it, in organic chemistry, we mostly deal with arrows that only involve the flow of two electrons, but we have to also learn about radical arrows too. All right, well, let's move on from here. It says, recall the orbital hybridization in carbocations and carbanions. So this is just a little bit of review. It goes all the way back to your Gen Chem days, really. But if you have a carbocation, so this is a carbon with a positive charge, it has an empty p orbital, right? Then you have 1, 2, 3, of course, sp2 hybrid orbitals, but it's got an empty p orbital, and thus the molecular geometry of the carbon in a carbocation is trigonal planar. It's flat. That's why they have this kind of, looks like a piece of glass or something here, okay? Just show that it's flat, okay? Flat as a pancake. That's the molecular geometry. However, when you have a carbanion, well, we know that the molecular geometry then is trigonal pyramidal. Why would that be? Because you have a pair of electrons in the fourth orbital here, which is an sp3 hybrid orbital. So you have 4 sp3 hybrid orbitals. What would you get? Like let's say you have methane. You've got 1, 2, 3, 4 bonds to it. Well, you'd say that's tetrahedral, but if you replace one of those with a lone pair, remember that molecular geometry only considers bonds. So we're only considering the carbon being bound to 1, 2, 3 things, and therefore it is trigonal pyramidal. And if you're saying, well, why are you spending so much time talking about carbocations and carbanions? I already know both of these. Well, think about it. A radical somewhere kind of in between the two, right? Because you've only got one electron. Okay, so let's see what it looks like. These radicals appear to actually be trigonal planar, like they're sp2 hybridized, or you can think of it as a shallow trigonal planar that's just kind of flip-flopping, whoop, 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 and it makes that sound when it does it. But anyhow, it's like rapidly inverting shallow pyramids, or you can think of it as being trigonal planar. Well, I'm here to tell you that in this class, okay, so in Chemistry 3101, we're always going to treat the molecular geometry of a carbon radical as being trigonal planar. Okay, so I'm going to write a little note here. CHEM 3101 is always going to treat a carbon radical as if it is flat. Okay, it's trigonal planar. Cool? And the reason why you need to know that is because there's going to be some stereochemical consequences because of that, as you can imagine, just like we saw when we looked at ionic mechanisms. Okay, so now that we've got that, we know we have a single barbed arrow that represents the flow of one electron. You can make a radical. Then we talked about a carbon radical being trigonal planar, so it's flat, or we treat it as if it's flat. Let's talk about radical stability. I got some good news for you. If you remember carbocation stability, it follows the same trend as radical stability. It says free radicals, I'm just reading from right here, free radicals do not have a formal charge, but are unstable because they have a complete octet. And if you're thinking, well, how can you have those two things? Look, let's go over that quickly, okay? Let's say you have a methyl radical. So there is a carbon here, okay? What's the formal charge on the carbon? Formal charge is equal to the number of valence electrons the carbon has, which is 4. Subtract 1, 2, 3 sticks. Subtract the number of dots. You've got 1 dot. So 4 minus 3 minus 1 gives you 0. So there's no charge on the carbon radical. It's uncharged. However, that carbon doesn't have a complete octet. Let me prove that to you. If you look, okay, it's surrounded by what? 1, 2, 3, 4, 5, 6, 7 electrons. Okay, again, none of these radicals have a formal charge, but they all have an incomplete octet, so none of them are stable. Or they all have some instability associated with them, I should say. Radicals are going to follow the same stability trend as carbocations did, as they're both electron deficient, right? They're both missing electrons, so it makes sense that they follow the same trend. If you have a group that can donate electrons towards the free radical, it's going to help stabilize it. Hopefully you remember that when we looked at carbocations, the more R groups that surrounded the carbocation, the more stable it became. The same rationale applies here. We have more R groups surrounding our radical, it becomes more stable. Why? Because the R groups donate electron density via hyperconjugation. Okay, so they're donating electron density in this direction, which serves to stabilize the carbon radical. Thus, the conclusion is a tertiary radical is more stable than a secondary or a primary, and then a methyl is the least stable of all of these. If you remember, going all the way back to chapter 6, okay, so this is a few weeks ago. In chapter 6, do you remember we looked at enthalpies of reactions, delta H for a reaction, and we looked at calculating delta H for a reaction using bond dissociation energies? Well, those bond dissociation energies that we looked at in the tables, and we're going to look at some more today, those represent the homolytic cleavage of bonds. Okay, so each atom takes an electron. All right, so homolytic bond cleavages are where we get our bond dissociation energies from. Thus, it makes sense that bond strength is inversely proportional to carbon radical stability. The more stable the radical is that's formed, the weaker the bond is, right? If we look at just a couple of examples here, if you were to, let's say, break this bond between this carbon and this hydrogen, you would end up with a tertiary radical. I'm just going to draw the bond line structure. You'd end up with a tertiary radical. Well, it makes sense that this bond is only 380 kilojoules per mole compared to this carbon-hydrogen bond, which is 435 kilojoules per mole. Why? Because when you break this bond, you end up with, son of a gun, you end up with a methyl radical. So you have the carbon not surrounded by 3 R groups, it's surrounded by 3 hydrogens, which don't donate next to any electron density. So give me a thumbs up if you follow me. The more stable radical would be produced, the weaker the bond. The bond is more willing to break because you end up making something that's more stable. That's the rationale there. Sometimes students will get it backwards, but remember, the more comfortable the bond is being broken, well, the weaker the bond will be. It's like, I don't care if I break, I'm cool, All right, well, let's move on from there and let's talk about free radical resonance. If you go all the way back to chapter 2, we spent a whole a couple of classes just going over resonance structures. And just like a carbocation is stabilized by resonance, radicals are also stabilized by resonance delocalization. Fishhook arrows can be used to represent all the possible resonance forms. So let's take a look here. Just like an allylic carbocation had a resonance structure, and I can just refresh your memory, this is just chapter 2 stuff. We said, okay, well, the pair of electrons is actually shared. Those are delocalized over all 3 carbons. And so we have these 2 resonance structures in the hybrid. Well, if you have an allylic radical, you can draw these 3 arrows here, which show that radical is delocalized across the entire molecule, and you see it over here on this carbon on the end. So what I want to do now is practice drawing those arrows. If you just zoom in here and see what's happening, look, what happens is to make a bond, because you're going to end up making a pi bond where what I have circled here, you're going to take 1 electron from the radical, but you're going to have to take 1 electron from the pi bond. But the pi bond had 2 electrons. Where does the other one go? It's going to go over here like this to form the other allylic radical. Give me a thumbs up if you follow me on the arrows. Or are there any questions about those arrows? Because we're going to put them into practice, and we're going to look at a problem now where we have a benzylic radical, and we're going to look at the resonance structures of that benzylic radical. Just like carbocations, the more resonance delocalized a radical is, the more stable it is. Remember, electrons are like hyperactive children. If you give them more room to run around, supposedly they'll calm down, they become more relaxed. So a radical is the same thing. If you give it more space to be delocalized, it's going to increase the stability. So if you have a benzylic radical, which is, hopefully you remember what a benzylic carbon is. This, what I'm highlighting in yellow, that would be the benzylic carbon. If you have a benzylic radical, it's going to be stabilized by resonance where it can be delocalized across or around the entire ring. Let's take a look at the first view. Okay, so we have this is the benzylic radical. Then we make a pi bond here. You're going to move 1 of the electrons from the pi bond to this carbon on the top. You end up with this resonance structure. Now the curved arrows are drawn for us again. We make a new pi bond here, and we put the radical over here. So let's draw what that structure is going to look like. Let me get my pencil here. It's going to look something like this. We've got this 6-membered ring, like this. We didn't touch that double bond. We didn't touch this double bond. But now we have a double bond here, and we're going to have the radical down here. But look, now we have another allylic radical. So let's draw another resonance structure. What are we going to do? We're going to take 1 electron from the radical. Well, it's only 1 electron. We're going to take 1 electron from the pi bond and make a new pi bond, and we're going to take the other one and put it here. And let's draw that next resonance contributor, which is going to look like this. And now we've got 1, 2, 3 double bonds, and we have the radical up here. And that is, I think, technically the last resonance structure that we need to draw. I mean, we could finish it out. Let's just draw one more where we put that benzylic radical right back where it started, which was up here. And then we end up with something that looks like this. We have our benzylic radical right there. And now we've restored our aromatic ring. And there you have it, my friends, drawing the resonance structure of a radical. In this case, it's a benzylic radical. It's even more stable than an allylic radical, right? What we're saying here is that this radical is more stable than an allylic radical. Why is that? They both have resonance contributors, but the benzylic radical has all of these resonance contributors. Really, it's got a total of 4, whereas the allylic one, we said, had this one. Okay, and then we said we've really only got, well, we do only have one other one where you move the electron to the other side like that. And there you go. Everybody with me on that? Any thumbs ups there? Any questions about that? How did you draw those arrows? How dare you draw those arrows? I don't like these arrows. These arrows look funny to me. No? Okay. All right. Well, look, we said that the benzylic radical is pretty darn stable because it's got all these resonance contributors, right? And then we said, well, the allylic radical is also pretty stable because it's delocalized. Both of those, as a matter of fact, are more stable than a tertiary radical. So both of those would be more stable than this. You have a tertiary radical like that, it beats both of them out. Okay, and you're thinking, well, come on, that's only a, primary carbon. Yeah, but it's resonance stabilized. And I have that summarized right here. This is just a picture taken straight from our book, that the benzylic is kind of the king of the castle in some ways. Then you go to allylic, then you have tertiary. So if the benzylic radical, again, if it's so darn stable, that's why a carbon hydrogen or a benzylic carbon hydrogen bond is so weak compared to an allylic, and then compared to tertiary, and so on and so forth, right? We go all the way down to the methyl, which we said was, really unstable. It was like 435 kilojoules per mole or something like that. Now, if you're wondering, and you probably are, but if you're wondering, could you have something even less stable than that? Even higher energy carbon hydrogen bond than a methyl? The answer is yes, you can. You have one that's not the king of the castle. It's like, super unstable radical, and that is a vinylic radical. Okay, just like we never drew a vinyl cation. So something you never see in organic chemistry is this: is if you have a double bond, you never see a positive charge on a double bond like that. That is a big no-no. That's a vinyl cation. That is a huge no-no. That is a sin. You can, be in serious trouble for drawing one of those. If somebody finds out, I'm just kidding. But those are a big no-no. So it should come as no surprise that if you were to try to break this bond homolytically, the vinylic radical like this, you would end up with a vinyl radical. And that also is super duper unstable. Okay, you're never going to have a radical on an sp2 hybridized carbon, just like, or I should say a vinyl carbon, and you're never going to have a carbocation on a vinyl carbon. Doesn't happen. Okay, super duper unstable. So those are kind of things that everybody needs to know. We're kind of learning the language of radicals right now, the arrows, the stability. And if you're wondering why we need to go over the stability, well, they come up, when we're trying to draw the products of radical bromination, which we're going to look at the very end. You're going to need to understand, oh, this bond is weaker than this one. This bond is stronger. So it will come up a whole bunch of times. With all that in mind, let's take a break here and try a practice problem. Well, that's not a break. Well, let's try it anyway. So it says here, rank the following radicals in order of stability. Okay, so let's see here. A. What if we call this one, I'll call this one 1, 2, and 3. Could anybody tell me which one of these would be the most stable? Would it be 1, 2, or 3? Yes, my students are 100% correct. So I'm just going to write here, I'll put most stable. Which one would be the least stable? Anybody? Which one's just not stable, not happy? Yeah, absolutely. So number 1 would be the least. So we'll put least stable here. Then we'll put the middle one as being the most, and then the other one is somewhere in the middle. Why? How did my students answer that so quickly? So if you're confused, if you're like, how did they get that? This radical, one that's the most stable, is a tertiary radical, right? This carbon is attached to 1, 2, 3 carbons, whereas the least stable one is a primary radical. So we have tertiary and we have primary. And then the other one is somewhere in the middle because it's a secondary. Let's try it again. What if I call these ones 1, 2, and 3? Which one of these would be the most stable? Yep, absolutely. Yep. My students are all 100% correct. This would be the most stable because it's tertiary. This one is tertiary. Which one's the least stable? Anybody? Yeah. And I know you knew the answer. Yep. This one would be the least stable. All right. That's it, my friends. Usually students do very well on questions of carbocation and radical stability. So let's move on from there. Let's try a little bit of resonance practice. Again, as I told you in chapter 2, resonance structures are not something that can be mastered by watching somebody else. You've got to try it on your own. Can't be afraid to make a mistake, and then you'll be able to draw some resonance structures. So let's start with the first one, C. You can see that we have an allylic radical right here. All right, we have the double bond, the adjacent carbon, and there's a radical on it. So we can start with some curved arrows here, like 1, 2, and 3. Can maybe make that a little neater, like that. So that'll give us our first resonance contributor, and then we'll see what we have. When the dust settles, we've got a new pi bond here, and we have our radical up here. Can we draw another contributor for this one? Yes or no? Would it be possible to draw another contributor for this one? Do we have another allylic radical in here? Yeah, thanks, Clinton. Absolutely. He says, yes, I agree. You have an allylic radical right here. So we can draw another resonance contributor. We're going to make a new pi bond, and we're going to put the unpaired electron right here. Like that. Let's scribble that down and see what it looks like. Looks like this. And that is the last contributor. We have no allylic radical after that one. Okay, this next one is kind of an interesting one. I'll just go over it a little bit quicker. So here you can see that you do have an allylic radical here. This double bond is not allylic to the radical, but the double bond in the ring is allylic to the radical. Let's draw our resonance arrow. So 1, make a double bond. We put the unpaired electron up here, and we end up with a resonance contributor that looks like this. So we have the double bond down here. There. But there are no other resonance contributors that can be drawn in this case. This is the end of the road. There's only one. The reason why is because the unpaired electron, this unpaired electron is not allylic to terminal double bond. We'll just call it terminal alkene. This is the terminal alkene, right? Because it's at the end of a line, okay? It's not allylic to that, so we cannot draw any resonance contributors that bring that double bond into play, so to speak. All right. So resonance structures. Let's try one more. Here we go. This one's kind of an interesting question. It just says identify the weakest bond. You are the weakest bond. I couldn't help myself. Let me just highlight a couple of protons here. What if I put this proton in red, and I put this proton in blue, and I put, I don't know, I'll put this proton in green. Could anybody tell me which one of these would be the weakest bond? Would it be the red one, the blue one, or the green one? And we're looking for the weakest carbon-hydrogen bond. Which one would be the weakest? Absolutely, yes. Great work. Yes, it's the blue one, isn't it, right? Because that one is allylic, right? This is the allylic carbon, so this is an allylic hydrogen. And if you break that bond, homolytically, then you end up with an allylic radical. Have this. Here we go. Beautiful. That's really great. This is tertiary allylic, so that's very, quite a weak bond. Let's try the next one. What if I highlight this proton in red, this proton in black, and this proton in blue? Let's do that. And then I'll highlight this one in green. Okay. Which one of those would be the weakest bond? The red, the black, the blue, or the green? Absolutely. Yes. Right, because the green one and the blue one, they're both allylic. However, or sorry, the green one and the black one are both allylic. However, if I break the black one, then I end up with something that is tertiary allylic. Right? This is tertiary allylic. If I had broken the green one, which would be wrong, but if I did that, then you'd end up with this, which is still allylic. Oops, I put radical in the wrong spot. But this is only secondary allylic. Secondary allylic. All right. In fact, it's double allylic, really. What about this one? I put a lot of problems on here. What if we try this one? We'll just try one more. I'll put this one. I'll put this one, and then yeah, I'll just pick both of those. Which one's a weaker bond? The red one or the blue one? And remember, there's no trick questions in Mr. Dion's class. Yes, absolutely. My students, okay, you guys get it. Students are great. Okay, it's the blue one. I should highlight these maybe. So here it was the black one. Here I'll remove that. And then here it's going to be this one. All right, so let's just draw the radical for the fun of it. This is our radical, and like that. And in this one, it's going to be this bond here, which should be the weakest. All right, there we go. That's enough of that. Let's move on from there, and let's talk about patterns in radical mechanisms. This is very different than the ionic mechanisms that we've looked at before, SN1, SN2, E1, E2, something completely different. But like ionic mechanisms, radical mechanisms do follow some patterns. If you follow along with the patterns, you'll be able to get it straight pretty quickly. It says, you know, even though the radical mechanisms do follow patterns, they're very different from the ionic ones, okay? For example, we'll start with carbocation rearrangement. Remember that, the whole methyl shift and the hydride shift? Well, radicals don't rearrange, okay? If you had this this secondary carbocation, you know that you'd get a methyl shift this way, okay? So that you would end up with, this tertiary carbocation. However, you get no rearrangement with a radical. What you see is what you get, okay? Remember, resonance and rearrangement are two different things. Okay, you can have resonance, but you can't have groups shifting like a methyl or a proton. And when we're looking at radical mechanisms, there are 6 key arrow pushing mechanisms that come up over and over and over. The same 6 patterns show up time and time again. So let's review them, or let's go over them, I guess. I'm going to kind of go over them a little bit quickly at first, just to introduce them to you, and then we're going to kind of look at some similarities. Then we're going to get into them in even more detail. Okay, so this is kind of an intro. Number 1 is called a homolytic cleavage. This is where you take a sigma bond and you just break it apart, and you end up with a pair of radicals. So homolytic cleavage. And if you're thinking, isn't that what you showed me in the first slide? The answer is yes. Okay. Those are usually initiated by heat. And for heat, we use the little triangle symbol. And for light, we use the little H nu, because E is equal to H nu from Gen Chem 1. The next one is addition to a pi bond. If a radical comes in proximity to a pi bond, you can make a new sigma bond, and then you form a radical, so addition. The next one is hydrogen abstraction. It's exactly what it sounds like. It's ripping off a proton. So if you have a molecule with a proton and the radical takes that proton so that you end up with a new radical, well, that's hydrogen abstraction. The next one is halogen abstraction. If you take a radical and it reacts with Br2 or Cl2, and I'll explain why just those two later on, you can form a new R halogen bond and a halogen radical. So that's halogen abstraction. So hydrogen abstraction, halogen abstraction, they usually occur in that order. The next one is an elimination. Elimination is actually the reverse of the addition. Okay, addition was really nothing more than a radical plus a double bond gives you a sigma bond and a radical. Elimination is where the radical fragments to give you a double bond, and you end up with a radical. And the last one is a coupling. A coupling is probably and I don't like to use the word easy in organic chemistry, but it's probably the easiest of all the mechanisms. It's two radicals meet together and they make a bond. Okay, so you just draw the arrows, you know, meeting on the middle of the street here or something, and they end up making a new sigma bond. That's coupling. All right, so it's the reverse of homolytic cleavage, which was when you took this and you broke it apart and then you made that. Okay, so you might have noticed a couple of patterns here, very distinctive patterns, and that is that you can actually group these in kind of 3 or 4 processes, you know, if you want to think about it that way. You probably noticed that the homolytic cleavage, the first one, and the last one, the coupling, are just the opposites of each other. And if you notice that, you're 100% correct. They are the opposite of each other. Then you might have noticed that the second one that we looked at and the fifth one, the addition to the pi bond and the elimination, those are the opposite of each other. That is also true. Then the hydrogen abstraction, well, that's not the opposite of a halogen abstraction. That's something new unto its own. But a hydrogen abstraction, one way or the other, is still a hydrogen abstraction. And then a halogen abstraction, again, is something unto its own. So you can kind of break it into 4 patterns, really, the way I look at it. Anyhow, there we go. So halogen abstraction isn't on here, but again, it's kind of its own thing. You know, you take your halogen, okay, so I'll just add it to the list here. So halogen abstraction, halogen abstraction, just like that, is where we end up with, you know, XX plus a radical, okay, and that's also, again, unto its own kind of thing. Okay, so there we go. That was pretty quick. Now let's look at them in more detail. Okay, the steps in the radical mechanism, those 6 steps that we looked at, those can also be classified according to these 3 terms. We can call them either an initiation radical mechanism, a termination, or propagation. These are what we're going to talk about all the time, is either initiation, termination, or propagation. Initiation, as you can imagine, that's starting off, so that's the start or initiating. Termination is the end. That's when it's done. So this is like the first step. This is going to be the last step. And then propagation is like propagating something. It's like kind of the middle. So we'll put propagation is kind of like the middle. And this is just in quotations, all right? So what it means by initiation really is starting off. Well, what's starting off? It means you're starting with something that isn't a radical, and then you're making a radical. So that's initiation. You start with something that is not a radical at all, and you just make a radical out of it. So initiation is homolytic cleavage. You start with a non-radical, you break it apart, you make a pair of radicals, so initiation, homolytic cleavage. Propagation is any mechanism where you start with a radical and end with a radical. It's always the same thing. Look, addition to a pi bond, you start with a radical, you end with a radical. If you have a hydrogen abstraction, you start with a radical and you end with one. And you see the same thing occurring for halogen abstraction. Those are all propagation steps. In elimination, sorry, I forgot to include that, you start with a radical, end with a radical. All of these have that in common. Starting with a radical, ending with a radical. That is propagation. How do you know when your radical mechanism is done? Well, that's going to be when you annihilate your radicals. Yes, we use the term annihilation, okay? So termination is when 2 radicals meet together, they couple, and you end up with something that isn't a radical at all, right? You have 2 radicals, they meet together. Well, they're not going to make a radical, they make a bond. So that is what termination is. So we've got all those 6 patterns that we looked at. Now we're classifying them as being either initiation, propagation, or termination. You can imagine that as we get further on in the material in this chapter, the reactions that we look at are going to start with some kind of initiation, then they're going to have some propagation steps, and then there's going to be a termination to kick it all, to end the whole thing. All right, initiation, propagation, termination. That's a lot of information. Initiation, propagation, termination, information. No, that's not part of it. Anyway, it says draw the appropriate fishhook arrows for each of the following radical processes. You can see that the first one, 10.8a, is a propagation because you're starting with a radical and you're ending with a radical. Let's take a look. What's going on here? The first thing we need to do is redraw our HBr molecule. I don't want to see anybody doing stuff like this where you're like, I'll just draw a line in between the two. Well, that looks like terrible. So you need to redraw the Lewis structure of the HBr. And then we're forming a bond between the carbon, what was the carbon radical, and the hydrogen from HBr. So we're going to need to take one electron here. And then these electrons are actually going to kind of meet, you know, in the middle like this. And this represents the formation of a bond, right? You have the one radical coming out, and then the other one comes up to it like this, and they connect to make a bond. This is bond forming, right? And then the other radical is just going to end up on the bromine. So we end up with a bromine radical, and this is the carbon-hydrogen bond that we formed. This reaction that we're seeing here, this would be a hydrogen abstraction. How do you know that? Because your radical grabbed a hydrogen. So hydrogen abstraction. Oops, what did I do here? There we go. The next one, we have a pi bond, we have a radical, and then we're adding the radical to the pi bond to make a new radical. So this must be addition to a pi bond. What's that going to look like? Well, we're going to start with our bromine radical, and we're going to take one electron from the pi bond. This represents the bond being formed. And then the other electron is going to end up here like that. And there you have it, my friends. 2 reactions with all the curved arrows drawn for a radical mechanism. Is everybody with me on that? Or are there any questions about the free radical mechanisms? Will they need to be practiced? Of course you will need to practice them. Okay, everybody needs to practice them. But that in a nutshell is how you draw the mechanism, a radical-based mechanism. Initiation, propagation, termination, and then we looked at these 2, propagation steps here. Okay, well, with all that in mind, let's go to the next section, section 10.3. You're going to have to pay close attention on this spot because we're going to talk about enthalpies a little bit in a few minutes. Let me see here. Yeah, maybe not right away, but we're going to in a few minutes. So you're going to have to follow me on the chlorination of methane in order to understand the next section. So bear with me here. What is the chlorination of methane, first of all? Well, methane, hopefully you remember from chapter 4, it's the simplest possible hydrocarbon you can have. It's just plain old CH4. Okay. If you take methane gas and you treat it with chlorine, just Cl2, you put some light, because you know that light helps to initiate a radical mechanism. What you end up doing is, here you have 1, 2, 3, 4 bonds to hydrogen. You replace one of those carbon-hydrogen bonds with a carbon-chlorine bond, right? And you make this compound, which would be called chloromethane. So let me put the chlorine right here. You end up making this bond. Okay, so you call that methyl chloride, or you could call it AKA chloromethane. Either one is perfectly fine. Okay, and HCl is also produced. Let's take a look at the mechanism of the chlorination of methane, keeping in mind it's going to be 3 steps, or three stages, not steps, 3 stages. Initiation, propagation, and termination. What's initiation? Well, initiation is going to be homolytic cleavage. It's the chlorine that breaks apart homolytically to make a pair of chlorine radicals. So that's our first step, initiation, and we end up with some radicals, and now we can get the ball rolling. In the propagation steps, the first one is going to be hydrogen abstraction, followed by halogen abstraction. Let me back up and show you something before I get into this. Something I forgot to say. Just because chlorine can be broken apart by light to make 2 radicals, that does not mean that every single molecule of chlorine is going to break apart to give you a pair of radicals. Some of the chlorine will break apart to give you some radicals, but not all of it. So you're going to have both chlorine radicals and you're going to have Cl2 in your reaction mixture. Thus, when you look at the first step of the propagation, it's hydrogen abstraction. The chlorine radical is going to rip a proton off to make HCl, and then you end up with the methyl radical. Okay, but remember, we need to add a chlorine there. So the methyl radical is going to react with some of that chlorine that hasn't been converted into radicals. Again, only some of the chlorine is converted to radicals, so you still have Cl2, as I have shown in the yellow oval. You do a halogen abstraction, and then you make another radical. Now, these two steps are very important, and we're going to come back to them in a few minutes. Termination, the last part, because we've already made, this is our chloromethane. This is it. It's done. Chloromethane. So to end everything off, to end the whole process, what do we have to do? Kill our radicals, annihilate them. So what do? We have two radicals coming together. This is usually the student's favorite step, because I will accept any two radicals that are produced. You show any two radicals coming together to make a non-radical, and it counts. So it could be the two chlorine radicals. It could be the methyl radical and the chlorine radical coming together. It could be two methyl radicals. I don't care. They all work as long as two radicals meet on the street. I got to stop saying that. Two radicals come together and they make a non-radical. It counts as termination. Good? All righty. That was the whole mechanism for the chlorination of methane, right? First step was initiation. Propagation had two steps. One was hydrogen abstraction. Two was halogen abstraction. I remember this because hydrogen is element number one and the halogens aren't element number one. That's kind of my way of remembering that hydrogen abstraction is first, then termination. Okay, if you're very astute, and I think it would be tough to notice this, but you might have noticed that if you tally up the two propagation steps and you cancel what's the same on both sides, for example, the chlorine radical is the same on both sides, as is the methyl radical the same on both sides. You tally that up, and the net reaction you get is the net reaction for the whole thing. Methane plus chlorine gives you methyl chloride plus HCl. So the propagation sum, or when you sum them together, you get the net reaction. And what else? It says propagation is a chain reaction because the products for a later step serve as the reactants, right? So all it's saying here is nothing more than this. Let me tell you. You end up producing a chlorine radical in the second step of the propagation, but you need it for the first step. So it kind of keeps going and going and going over and over like that. Well, when you think about stability of a radical, if we think about the radical that would be produced from methane, so a methyl radical would be this. And I told you this is super unstable, if you were to break that. Well, you can imagine that if you replace one of those hydrogens with a chlorine, now it's going to have increased stability because this is going to pull electron density away. It's going to serve to stabilize that carbon a little bit. So what that does is it makes the molecule even more reactive when you have chloromethane. It's even more reactive than methane was. So what happens is, since you end up producing chlorine, you can guess what's going to happen. Polychlorination is just going to happen. It's going to make methyl chloride, but that's going to be even more reactive than this was. So it's going to chlorinate again. Then this methylene chloride is more reactive than methyl chloride. Then it keeps going and going until you get to carbon tetrachloride. So it's very difficult to just stop here. It's like a runaway train. It just keeps chlorinating and chlorinating and chlorinating because you get something that has a lower bond dissociation energy all the time as you add chlorines to the molecule. So in order to get monochlorination, what do? You just put a huge excess of methane. So there's so many methane molecules that the chances of what the radical has a higher probability of running into a methane molecule than a methyl chloride or anything else. Okay, that's kind of the workaround for that. Might not sound elegant, but it works. Okay. You should be able to draw a radical mechanism like is found in Skill Builder 10.4. So we're going to go over this mechanism in detail. It says, draw a mechanism for this reaction. The chlorination of chloroform to produce carbon 10. Let's go back here. So what we're trying to do is draw the mechanism of the chlorination of chloroform to make carbon tetrachloride. So what the expectation is that you can draw the initiation, the propagation steps, and the termination step. Let's begin. Okay, let me write down the players first, just so you're aware. So it's chloroform, CHCl3, plus chlorine gas, which is Cl2. Then we have our HNu, our light source. Then we're going to end up with carbon tetrachloride as our product plus HCl. Okay, let's start with initiation. So initiation. I don't know if I have enough space here, so we'll start with initiation. We have chlorine, Cl2. It's going to break apart, 1, 2, and you're going to end up with 2 chlorine radicals. I'll just put 2 times chlorine radicals. There's my unpaired electron. So propagation. Propagation. First step is going to be hydrogen abstraction. So what's going to happen is my chloroform molecule, so CHCl3, is going to react with the chlorine radical. I'm just going to put in the unpaired electron just to clarify things. So I'm leaving out all the other valence electrons just to make things a little bit more abundantly clear while we're learning the content here. I'm going to abstract this hydrogen. So make a new bond between the chlorine and the hydrogen to make HCl, and I'm going to make the CCl3 radical. So I end up with something that looks like this trichloromethyl radical plus HCl. So that was the hydrogen abstraction. Next, I'm going to have the halogen abstraction. And this is another propagation step. We're going to start with this radical. So let's draw it out. We have the CCl3 radical. Plus now it's going to react with Cl2 because remember, not all of this gets converted into radicals. We're going to form our carbon-chlorine bond. So this is going to make our carbon tetrachloride. And you can see how this is self-sustaining because we end up with CCl4. I'm not going to draw the Lewis structure. Plus we end up with another chlorine radical. There we go. The last step is going to be termination. So termination. You can draw any 2 radicals you want coming together. I mean, I could ask you, but we could just pick 2. We could just pick 2 chlorine radicals to make it simple. And we'll say they're going to come together like that. And reaction is done because you have no more radicals. Oops, I didn't mean to do that. There we go. You end up forming Cl2. If you look very carefully, you might notice that if you add these 2 reactions together, your propagation steps, that the trichloromethyl radical cancels and the chlorine radical cancels. Look, we end up with CHCl3 plus Cl2 gives you CCl4 plus HCl. We end up with the net reaction. So the sum of your propagation steps should be the overall reaction, and that is the whole mechanism. Normally when I give paper quizzes in the spring or the fall semester, I'll ask this question or something like it, and I'll say you must draw all the initiation, propagation, and termination steps, along the way, and I can ask little tidbits about it. But make sure you practice this, that you're aware of how to draw this, and don't fall into the trap, and I know you don't, or I know my students don't. My students are great, but don't fall into the trap of thinking, oh, well, I'm taking this class because I want to do a good job on the MCAT, next year or something, and they're not going to ask this. Well, this is exactly the kind of stuff they ask, kind of the last chapter of the semester, were you still paying attention when you were super tired? I don't know. That's the kind of stuff they love to ask, Anyhow, let's talk about these initiators. The initiation is where you start with a radical and then or a non-radical, sorry, and then you end up with a radical. For radical initiators, I mean, we saw a dihalide like chlorine, but do you remember when we looked at the conditions of HBr and ROOR? And I said, we're going to cover this mechanism in chapter 10. Well, I wasn't being facetious. And the reason you use an alkyl peroxide is because it's such a good radical initiator. So this Anti-Markovnikov addition of HBr across a double bond is a radical mechanism that we're going to look at in detail. You can see that's an even better radical initiator than chlorine because the bond dissociation energy is even lower. Then you get to this thing here. This is called an acyl peroxide. This bond between these two oxygens is really weak. It's only 121 kilojoules per mole to break that. And the reason why is because you end up with a radical that is resonance stabilized, okay? Anyhow, there we go. Nothing to it than that. Acyl peroxides. What's next? The whole section on radical inhibitors. I'm not really all that worried about radical inhibitors. We could take a quick peek at it. A radical inhibitor, you can imagine, is something that prevents radicals. It says they react with radicals and prevent the chain process from initiating or propagating. And what makes a good radical initiator? What's something that's going to gobble up radicals or consume them so you don't have them? Well, it says that a stabilized radical or a compound that forms a stabilized radical, those are good at getting rid of them. For example, oxygen is actually a diradical, and so it can react with 1-2 other diradicals. And then this molecule here, which is not a bad idea to memorize, hydroquinone. I think everybody, well, maybe not. I don't know if I taught you an aromatic ring with a hydroxyl on it. That's called phenol. But if you have another hydroxyl at the opposite end, that's called hydroquinone. Hydroquinone can react with 2 radicals, and I'll show you why. I think right here, I think I put it in. Yeah, hydroquinone is great because if it reacts with a radical, it'll make a radical on one side, and then you can do the same thing on the other side. So you end up with this diradical, and then you can show how that is actually benzoquinone. Okay, it actually has, or you can show the electrons moving around to form benzoquinone. Anyhow, so that's kind of cool. And you could even try to draw the mechanism of that if you wanted to. You can say, well, I'm going to take this electron, make a double bond here. I'll put this one here, take this one here to make the double bond. I'll make a double bond here, and there you go. So that's the mechanism of the formation of benzoquinone. So what did we have? We had 2 radical inhibitors. Oxygen is one, and hydroquinone is the other. Only 2 that I would ever ask you about. Okay. The next section deals with halogenation and the thermodynamics of halogenation. So we're getting back into delta G, delta H, delta S, all that good stuff. So I think this is a great time to take a short break.